Today I'd like to show you a counterexample to Cantor's diagonalization argument that says that the real numbers are not countable. So the gist of the proof is proof by contradiction. So if you can put all the real numbers between 0 and 1 in an ordered, so for example, say the first number is 0.1111 ... and the second number is, let's just say 1000 ... and the third number is, let's say 1/3 3333 ... and then this is a countable series. That the premise of his argument is if you take the diagonal numbers and you add 1 and mod it by 10, you can create a new number where you'll have 2 1 4 ... and by definition this won't be in this set. So to get around this problem, what I've done was I've created a little function here that says while I equals 1, and then it goes into this infinite loop, and it says if I equals x, then it returns an error, and otherwise this print line shows basically is saying, okay, take this number along the diagonal and add 1 and mod 10 to it, and then go to the next digit. So if we put this in here where x is equal to 1, it would start out and saying, okay, I is 1, and while this is true, and then x is equal to 1, so it'll return an error. So now when we go into spot 2, it'll start when I is 1, and it'll find that it won't return an error because x is 2 and I is 1, and then it'll print out this first digit, which will be 2, and then it'll get incremented, and then x is 2 and I is 2, and then it returns an error. So basically every time it goes down the list, it will get one more digit before it returns an error. So the key to this now is how we build the list. And let's just name this M. Okay, so we start making our list by taking M, and that's going to be our whole list. Next, we take N1, so this will be step 1. Step 2, we put N1 in front, and then we have M. And step 3, we take N1, and then we stick N2 after that. And so we keep going down the list, and now we have the magical ... So we have N1, N2, N3, ... and we have M at the very end. And so since M is not in, it's at the very end of this list, which whatever that means, but it does not have a counting number associated with it. So it will never, when it runs this code at the very bottom of this list, it will never return an error. It will just print out an infinite number of digits along here, like our function, like our number x here, and it won't ever return an error. So now we've created this list from this list and added this number, which wasn't supposed to be in there, but it is now, and you can always add one element to an infinite set and still have it be infinite. So this is still countably infinite, but it's got one more number in it, which is the number that it said what couldn't by definition be in here. So this contradicts Cantor's diagonalization proof. And that's all I have for you. Thanks. Always awkward.
that's all for today. Bye.